Hello everyone. So today we are going to start digital communication, and you know that every year around 3 to 4 question comes from digital communication. 6 to 7 marks come in GATE exam from digital communication. Okay. So it comes around 3 to 5 question every year. Sometimes mostly it comes 2 marks question in digital communication because questions are big and lengthy. So we will start with some basic like bandwidth calculation and the bitrate calculation, and after that we will study about the digital means carrier modulation schemes like ASK, PSK and FSK. So let's start with the basics first. The first thing we will study today is the bit duration. Bit duration is denoted by duration of bit, so it is denoted by TB. Okay, and let's suppose there is one sample. See, this is our now signal, and signal is denoted by this. Okay, the bit 1, this is bit 1 and this is bit 0. Okay, this is 0, this is 1, this is 0 and this is 1. So like this it is given, this signal is given 0 1. So let's suppose there is 2 bits is required for denote a symbol or sample. This means that symbol S1 is denoted as 0 0. So here is 2 bits to denote the symbol S1 or sample S1. So this whole duration is the symbol duration. So that is TS, because 2 bit is required. Let's suppose symbol S2 is denoted by 0 1. So this is our symbol S2. So there is 2 bits per sample, so this is our symbol duration TS. This is 2TS. Okay, so now what is the value of TS is our symbol duration, and there is bit 1 and this is bit 2. So this duration is TB and this is also TB. So TS is equal to TB plus TB, that is equal to 2TB. Okay, when n is equal to 2. Now let's suppose n is equal to 3 bits per sample, means each sample is denoted by 3 bit. Like let's suppose sample was S1 is denoted by 001 or S2 is denoted by 002. In this case the symbol duration TS, that is equal to 3 into TB. Okay, so it will be 3 TB. So from this what we got an important result that symbol duration TS, that is equal to n into TB. Here n is the number of bits for representing each sample and TB is the duration of each bits. So our TS is equal to n into TB. So this is very important formula. So let's come to the new formula. We will derive from this formula only. TS is equal to NTB if it is given. Then what we can do, we can write this as 1 by TS, that is equal to n by, sorry, this TB will come this side, so 1 by TB, that is equal to n by TS. And we know that 1 by TB, this is called the bit rate, that is denoted as RB. This is also known as bit rate. Okay, and 1 by TS, the reciprocal of symbol duration, that is Fs, that is equal to sampling frequency. So here we got RB is equal to n into Fs. Okay, so this is also one of the very important formula. This is bitrate is equal to n into Fs. Here RB is equal to bit rate, and Fs is the sampling frequency. So now let's come to the transmission bandwidth formula. What is transmission bandwidth? Transmission bandwidth is a bandwidth required by a symbol before transmission. So let's suppose the message signal MT is given. This is our message signal MT, and it is transmitted through a PCM system, PCM transmitter. So after converting this message signal into the digital equivalent, we got this, the encoded signal is like this. So this is now transmitted. Now let's suppose there is a rectangular signal, and this is means this is 1 bit, this is bit 1 represented as the high voltage. So when it is transmitted and this duration is, let's suppose, so when we will change this signal into the frequency domain, we will get like this. This is 1 by TB and this is minus 1 by TB. Okay, so our signal bandwidth, that is equal to 1 by TB minus 0, because signal bandwidth is the defined by the frequency deviation in the positive axis. So that is 1 by TB minus 0, that is equal to RB, because 1 by TB is our RB. So we know that channel bandwidth should be always equal to the signal bandwidth. So channel bandwidth, signal bandwidth is here RB. So channel bandwidth should be always equal to RB. So transmission bandwidth, that is the channel bandwidth required, that is equal to RB, and this is for the rectangular pulse. Okay, keep in mind, because for different kind of pulse the bandwidth is different, and we will study all about in this lecture. So this is for rectangular pulse. Transmission bandwidth will be RB, that is the bit rate. Bit rate is equal to N into Fs for rectangular pulse. Okay, up to this clear? So now let's take a question. A message signal of 8 cos pi into 10 to the power 5t is given to PCM system. Okay, now each sample is encoded with 4 bits and represented by using rectangular pulse. Now we have to find delta, RB and transmission bandwidth. So in this question, a message signal of is given, that is 8 cos pi into 10 to the power 5t. It is given to the PCM system for transmission, and the sample is encoded with 4 bits. Okay, and they represented by using rectangular pulse. So we have to find delta value, bit rate and transmission bandwidth. So for solving such question, what we will do, our message signal MT, that is given, that is equal to 8 cos pi into 10 to the power 5t. Okay, so now in this we got AM is equal to 8, and here FM is equal to pi into 10 to the power 5 divided by 2 pi, that is equal to 50 kilohertz. Okay, so what will be the sampling frequency with the Nyquist rate? Sampling frequency when nothing is given, that is equal to Nyquist rate, that is equal to 2 into fm, so it will be 100 kilohertz. Now we know that delta is the dynamic range divided by L. And what is n here? N is 4, so n is equal to 4. What is dynamic range? The maximum value of mt is 8 minus the minimum value, that is minus 8, divided by n is equal to 4, so we will write 2 to the power 4. So 16 by 16, that is equal to 1. So we got delta is equal to 1. Okay, now next is our bit rate. Bit rate is equal to n into fs. N is here 4 and fs is here 100 kilohertz. So what will be our bit rate? That is equal to 400 kilohertz. So we found our bit rate also. Now next is transmission bandwidth. Transmission bandwidth, that is equal to bit rate, and this is for this transmission bandwidth is only for the rectangular pulse. So we are using here rectangular pulse, so that is equal to RB, so that is equal to 400 kilohertz. So this question we have done. So now moving on to the next question. A message signal of 10 cos 2 pi into 10 to the power 5t is given to PCM system. This time sampling rate is 50% higher than Nyquist rate. Okay, so this is the only twist in this question, that the sampling rate is 50% higher than the Nyquist rate. Okay, maximum quantization error should be at most of 0.1% of peak amplitude of the message signal. We have to find the bit rate. Okay, so now in this question I will solve this question. Our message signal, that is given as 10 cos 2 pi into 10 to the power 5t. So what is FM message frequency? That is 10 to the power 5 hertz, that is equal to 100 kilohertz. Now the Nyquist rate, that is equal to 2 into FM, that will be is equal to 200 kilohertz. So the sampling rate, that is Fs is equal to 50% higher than the Nyquist rate. So Nyquist rate plus 50% of Nyquist rate. So it will be 150% of Nyquist rate. So it will be 3 by 2 into Nyquist rate. So that is equal to 3 by 2 into 200. So it will be 300 kilohertz. So this is our sampling frequency. Now our quantization error, the maximum quantization error, that is QE max, that is less than is equal to 0.1% of peak amplitude of message signal, that is AM. And what is our AM here? AM is this 10. So AM is equal to 10. Now QE max, QE is delta by 2. Delta by 2, that is equal to 1 by 2, and delta value is 2 into am divided by 2 to the power n. Okay, that is less than equal to 0.1 into am is 10 divided by 100. So this 10 will get cancelled, this 2 and 2 will get cancelled. So we got am divided by 2 to the power n is less than equal to 0.01. So what is our am is here? 10. So in the next page we will solve this question. So 10 divided by 2 to the power n is less than equal to 0.01. So now we will take this 2 to the power n that side, that will be greater than or equal to 10 divided by 0.01. So 2 to the power n is greater than or equal to 1000. So what will be the n value? So that 2 to the power n is greater than or equal to 1000. So n will be here 10. Okay. So for n is equal to 10, 2 to the power 10 is 1024. So now our bit rate, that is equal to n into fs. So the value of n is here 10, and fs we have 300 kilohertz. So our bit rate we got finally rb is equal to 300 into 10, that is equal to 3000 kilobit per second. There is one small modification, that the unit of bit rate is, it is not kilohertz, but sometimes it is given kilohertz. Unit of bit rate is kilobit per second. Unit of bit rate should be bit per second or bit per second. Okay, sometimes it is megabit per second, sometimes it is kilobit per second. So this question is done. Digital carrier modulation scheme. Okay, so what is this? This is the scheme of transmitting message signal with the help of carrier signal. So ASK, PSK and FSK are used to transmit binary sequence through free space. Why this is called as digital communication? Because the digital bits are transmitted. So, and how this is transmitted? This is transmitted through the channel, that is free space. What is the channel of digital communication? Free space. And channel of analog communication is wire channel. Okay, so it is transmitted through free space, and bit by bit transmission is there. Bit by bit transmission. Okay, means it is transmitted bit by bit. First of all, message signal is there, that is analog in nature, which is quantized and sampled to form the digital signal. Okay, and this digital signal is encoded and transmitted through the wireless channel, that is free space, and after that it is received by decoder, and the final signal is converted from digital to analog and it is received to the receiver. So this is the basic. So now we will start our first binary signaling schemes. This is binary signaling space scheme. Sorry. So in this, first we will study ASK. Okay, ASK stands for amplitude shift keying. Okay. So in ASK binary 1 means there is 2 bit, there is one, this is 1 bit signaling schemes and the 2 symbol is there. So it is represented by 1 bit, that is either 1 or either 0. So 1 is represented with the presence of carrier. If 1 bit 1, that is represented as presence of carrier. Okay, and bit 0, that is represented as absence of carrier. Up to this clear? So now we will study how this ASK is generated. So the next topic is generation of ASK, means how this ASK signal is generated. So I will explain this using the block diagram. So, and this ASK signal is also known as on off coding, because if 1 is there, then ASK is like this. Okay, this is 1, this is 0. So if 1 is there, then this is on, and when 0 is there, then this is off. Okay, so this is our ASK. Now how do we generate the ASK signal? So I will explain it with the block diagram. So let's suppose the message signal empty is given in the bit form like 101001 like this. Okay, it is given to the product modulator. This is our product modulator. Okay, so now I will tell you, 1 is represented as the 5 volt like this. Okay, and the 0 volt is 0, and again 1, then 2 times 0, then 1. You see, this is our signal. This is 1 0 1 0 0 1. So this is our signal. Okay, now the duration, this is known as bit duration, means duration of 1 bit. Now in product modulator, we give carrier signal CT using the local oscillator. Now what happened? This local oscillator produce a carrier signal, cosine signal AC cos 2 pi FCT. Okay, so up to this clear. Now when AC cos 2 pi FCT multiplied with 1, then when the message signal is 1, then our this output signal ST, that will be is equal to 1 into AC cos 2 pi FCT. So it will be AC cos 2 pi FCT. Okay, now when it is 0, then our output signal ST will be 0 volt. Okay, up to this clear? So when up to this clear, Now we will study about the demodulation of ASK. Before that, I will draw a diagram of message signal and what happens at the output end when it is received after multiplying with the carrier signal. So product modulator, I will tell you this. See, this product modulator multiply message signal into the carrier signal. So we will draw the waveform of ST, MT and CT. Okay. So our MT is like this: 1 0 1 0 0 and 1. This is our MT. Okay. Now what is our CT? CT is the AC cos 2 pi FCT. So it will be simply a sinusoidal signal like this. Okay, this is our CT. Now the ASK signal which is generated using the product modulator, it will be like this. So when there is 1, there will be the presence of signal. When there is 0, there will be absent of carrier signal. Now again it is 1, so it will be like this. Now again the carrier signal will be absent up to here. Now again it will be like this. So this is our ASK signal, that is ST. Okay, this is 0 and this one you can say that is AC, because the peak amplitude of CT is AC and AC into 1. So peak amplitude will be AC and the peak amplitude means negative side, the peak amplitude of CT is minus AC. So this will be minus AC. Okay. So this is the presence of signal. 1 represent presence of signal. Okay. And this 0 represent absence of, you can say, carrier signal also or signal in ASK. And ASK is also known as on off keying. So up to this clear. So now we will study about the demodulation process, or I don't think there is a need of demodulation process, but okay, we can study because sometimes it is asked in the GATE examination. They give the block diagram and they ask you the question. So the next topic what we are going to study is demodulation of ASK. And this is very important because demodulation process they ask oftenly in GATE examination. So what we do, see, we got our signal 1 as ST, that is equal to AC cos 2 pi FCT, and 0 as, this is, let's suppose, our S1T, S2T. Now we will give this to multiplier. Okay, we will study with the help of block diagram, and here again we will give the local signal using the local oscillator, that is AC cos 2 pi FCT. This is the demodulation process. Now see, when AC cos 2 pi FCT will be multiplied with, when signal 1 is received at the demodulation end, then this 2 will get multiplied and we will get AC squared cos squared 2 pi FCT. Okay, and when 0 is there, then we will get 0. Now we will pass this signal with low pass through the low pass filter. What low pass filter do? Low pass filter rejects the higher frequency component. Okay, Up to this. Clear? What does low pass filter do? It simply rejects the higher frequency component. Now when 1 is transmitted, then we will get the signal here AC square by 2. Okay, for 1. How we will get? I will explain you. For 0 we will get 0. How? Let's see. If 1 is received at the demodulation end, then this multiplier output will be AC squared cos squared 2 pi FCT. That is equal to AC squared. How you can write cos squared 2 pi FCT? You can write 1 plus cos 4 pi FCT by 2. Now this is passed through the low pass filter. What does low pass filter will do? This will reject the high frequency component, that is 4 pi FC here. Bandwidth is 2 FC. So this will reject this component and we will get output AC squared by 2. Okay. So when 1 is transmitted, low pass filter output is AC squared by 2. When 0 is transmitted, low pass filter output is 0. Now what we will do? We will pass it through this. We will pass this low pass filter output through the threshold comparator. Now the threshold comparator value, what it will be? It will be means there is some VTH assigned here. This VTH is equal to AC squared by 2 plus 0 by 2, that is equal to AC squared by 4. Okay, so now this is our V input and VTH is equal to AC squared by 4. So now if the signal is greater than VTH, I will give you here, if Vin is greater than VTH, then bit 1 is the output. If Vin is less than VTH, then bit 0 is the output. So understood how this demodulation process occurred at the demodulator end. Now if you have any doubt, you can ask me in the comment section. But there is one important thing, that assume local oscillator output that is equal to AC cos 2 pi FCT plus phi. This is our local oscillator output. So whenever 1 is transmitted, when you will expand the multiplication of AC cos 2 pi FCT into this and passing through low pass filter, you will get AC squared by 2 into cos phi. Okay, see this cos phi term came because of this phi. So now when phi is equal to 90 degree, then it will become 0. When phi is equal to 90 degree, then it will become 0. And for 0 also, for bit 0 also, output is 0. So we cannot receive, or we cannot distinguish the signal, which signal is transmitted. So in that time demodulation is not possible. So this effect, due to this phi, the demodulation process which is not possible, this effect is known as quadrature null effect. So just write a point. In ASK, we need to take carrier synchronization. Means carrier should be synchronized. There should not be extra phase component of phi. But if phi is equal to 90 degree, then what will be the output? Output will be AC square by 2 cos phi, so it will be 0. So output will be 0. So this effect is known as quadrature null effect. So ASK is affected with quadrature null effect. For removing quadrature null effect, we need to do the carrier synchronization. There should be no extra phase component, phi should be present. Okay, so up to this clear. Now we will see one more method of demodulation, that is, or detection of ASK, that is envelope detector. Okay, from here question came in GATE examination. Envelope detector or non-coherent detector. Envelope detector is also called as non-coherent detector. Okay, now we know that when 1 is transmitted, the signal is AC cos 2 pi fct. When 0 is transmitted, signal is 0. So now we will pass this signal ST to the envelope detector. Okay, so when we will pass to envelope detector, we will pass it through this now using the threshold comparator. So when we will pass to envelope detector just detect the output of that maximum output. So when 1, the maximum output is AC. When 0, maximum output is 0. So what will be the V threshold? V threshold will be AC plus 0 by 2, that is equal to AC by 2. So now if the threshold comparator output will be, if V in, this is our V in, V in is greater than AC by 2, then output 1 is decoded. If V in is less than AC by 2, then output 0 is decoded. So for ASK, this is a note point. For ASK, both coherent and non-coherent detection is possible. We have seen. If you have any doubt, you can ask me in WhatsApp anytime. If you watch lecture later also, you can ask me in WhatsApp that sir, I have problem in this lecture at this position. Okay, so now we will see the transmission bandwidth of ASK signal. So transmission bandwidth we will see now. I think noise is coming from fan, so I will slow down the fan. Okay, so now transmission bandwidth. So when 1 is transmitted, then our signal is like this. Okay, this is transmitted. So this is our bit duration, that is known as TB. Okay, so when we represent this in the frequency domain, we will get it like this. This will be our 1 by TB and this will be our minus 1 by TB. Okay, and when transmission of 0 is done, then we will get output as 0. So S2T is equal to 0. This is S2 S1T. So now what will be the bandwidth here? Bandwidth will be, okay, and now when this is multiplied with the carrier signal of FC, so we will get output like this. Okay, so this is our FC. This is FC minus 1 by TB. This point is, sorry, FC plus 1 by TB. This point is FC minus 1 by TB. Same on the negative part also. So what will be the bandwidth? Bandwidth will be higher frequency component minus lowest frequency component in the positive axis. So this will be equal to Fc plus 1 by Tb minus Fc plus 1 by Tb. So this Fc and Fc will get cancelled and we will get our bandwidth is equal to 2 by Tb. So this is the bandwidth of ASK, and so ASK bandwidth will be the bandwidth of ASK, that is equal to 2 by TB, and what we can write as 1 by TB is equal to RB. So that is equal to 2 into RB. That is the bit rate. Okay. So now we will study the energy per bit, EB. See, these things are very important. These things are useful later also while finding probability of error or bit error rate. So just keep in mind. So the next topic is energy per bit. Okay. So in digital carrier modulation scheme, each signaling point to be transmitted, that is either S1T and S2T, in this case of ASK you have seen, will have finite time duration and will be energy signals. See, our S1T or S2T, these have finite time duration, and you have studied in signal and system that when a signal is on the time axis, it is finitely expressed, then that signal is known as the energy signal. Okay, so there will be some energy associated with this. So when the transmission of one is happened, then our energy per bit EB, that is equal to energy of S1T. Okay, so what will the energy of S1T? It will be 0 to T S1 square T dt. And what is our S1T? That is AC cos 2 pi FCT. So it will be 0 to T AC square cos square 2 pi FCT. Okay, dt. Now we can write this cos square 2 pi FCT as 1 plus cos 4 pi FCT by 2. So we will get EB is equal to AC square by 2 0 to T dt plus 0 to T cos, sorry, here it will be AC square cos 4 pi FCT divided by 2 dt. Okay, so this, the first part integration will come AC square by 2 and this T, and up to what time duration it is durated? Up to TB. So we will put T is equal to TB here. So AC square by 2 into TB plus, see, this is the complete cycle. See, 4 pi FCT, so its period is 2 pi divided by its period is, means in one means 1 bit duration, it will take 2 complete cycle. Why? Because here it is 4 pi FCT, so it will take 2 complete cycle. So the 2 complete cycle integration of any sinusoidal signal will be 0, because positive part minus negative part, positive part minus negative part. So this integration will come as 0. So our EB is equal to, that is energy per bit is equal to AC squared by 2 TB. Unit will be joules for when transmission of bit 1 is done. Okay. Now when transmission of 0 is done, then our EB is equal to energy of S2T. So that will be is equal to 0. How? See, because S22 is 0. So if a signal is 0, then their energy is also 0. So now from this equation, we can find the AC also of the carrier signal. AC is equal to 2 EB by T, and that is under root. Okay. So we can find using the, means we can find AC also using this. So next we can see the constellation diagram of ASK signal. If you have any doubt, you can ask me anytime because I am available on WhatsApp also. So in constellation diagram, we have to represent the symbol S1 and S2 on the graph. So when 1 is transmitted, output is S1T, that is equal to AC cos 2 pi FCT, and we have already derived AC is equal to under root 2 EB by T. So that is equal to 2 EB by T cos 2 pi FCT. Okay. When 0 is transmitted, S2T will come, that is equal to 0 volt. So S1T is equal to root EB into root 2 by TB cos 2 pi FCT. On the same hand, S2T is equal to 0. Okay. Now when you see this under root 2 by TB cos 2 pi FCT, this is the orthonormal basis function. I will explain this in the next class, but for now you just assume this part as phi 1 t. Okay, so energy of orthonormal basis function is 1. Even you can derive the energy of this part is 1. Okay, because see, energy of this will be phi 1 t will be square of this, so it will be 2 by TB 0 to TB see, and cos 2 pi FCT we can square of cos square 2 pi FCT we can break into 1 by 2 plus cos 4 pi FCT, and plus the next part integration will be 0, so it will be, we'll get 2 get cancelled, so energy will be 1. So the energy of S1T, that is equal to EB, and we have already found only EB only is the energy of S1T. So when you will represent on the axis, let's suppose this is our phi 1t and let's suppose this is our phi 2t. I will explain you what is phi 1t and phi 2t in the next class, but I will write here phi 1t is root 2 by TB cos 2 pi FCT. Phi 2t is root 2 by TB sine 2 pi FCT. This is the orthonormal basis function. I will explain you what is this, and I will derive the proof also using the Gram-Schmidt theory in the next class. But today you just do the constellation diagram. So see, this part is S1T is equal to root EB into phi 1T. So it will be here, root EB from the origin, and S2T is 0. So S2T will be here. So this is our constellation diagram. This diagram is constellation diagram. Okay, and this is the distance between the symbols. Root EB is the symbol S1 and 0 is the symbol S2. So in next lecture we will continue from here and we will tell you what is the use of these things, and we will also find the other things. We will also study PSK, FSK in the next lecture. And today's lecture, if you have any doubt, you can ask me on WhatsApp or anywhere. And I will explain this, how this phi1t and phi2t came in the next lecture. So don't worry for now. Just leave this section now, because due to time constraint, I have stopped it here only now. Thank you so much for watching this lecture.